Welcome back to the deep dive. Today we're attempting something a little bit dangerous.
Dangerous.
I think so. We aren't just exploring a topic, we are trying to fundamentally break the way you see the world. And I don't mean that, metaphorically. I mean that after this hour, you might walk outside, look at a tree or a cloud or even the skin on your own hand and realize that you've been looking at a lie your entire life.
That's a bold opener. But you're right. We are peeling back a layer of reality today. We're trying to bridge the gap between the cold, rigid rules of mathematics and the messy, chaotic, organic world we actually live in.
And to get there, I want to start with a question. It's a question that I found in the source material. And honestly, it annoyed me at first.
Yeah.
Yeah, it seemed too simple. It felt like a trick question from a fifth grade geography quiz.
I think I know which one you're talking about.
The question is, how long is the coast of Britain?
Ah, yes. The coastline paradox.
Right. So when I first read this, I thought, okay, that's easy. I'll just Google it. I'll pull up Wikipedia or an atlas. Surely the Ordnance Survey or some satellite has measured this to the millimeter. There has to be a number.
And did you find a number?
I did, but then I found another number,
Yeah.
and then a third one. And they weren't just slightly different, they were wildly different. So here's the problem. Why can't we just measure the island? It's a rock. It's sitting in the water. It shouldn't be that hard.
It seems like it should be easy, right? You take a tape measure, you walk around the edge, you get a number.
Yeah.
This is where reality gets tricky. It's something known as the Richardson effect.
The Richardson effect.
Yeah, named after Louis Fry Richardson.
Yeah.
He was this eccentric Quaker mathematician and pacifist who was actually trying to figure out if the length of a country's border correlated to its likelihood of going to war.
Wait, really? He was looking for a formula for war based on geography.
He was. He didn't find the war formula, but he stumbled onto something much, much stranger. He noticed that when different countries reported the length of their shared borders, say Spain and Portugal, the numbers never matched. Spain would say the border was one length, Portugal would say it was another, and not by a little bit.
So were they lying, trying to claim more territory or something?
No, nothing like that. It turns out they were just using different rulers.
Okay, you have to explain that. How does the ruler change the length of the land?
Imagine you're trying to measure the coast of Britain. You decide to use a giant ruler, let's say a stick that is 100 kilometers long.
Okay, a huge measuring stick.
A huge one. And you walk around the island, laying the stick down end to end. Clunk, clunk, clunk.
Right.
Now, because your stick is so long it's clumsy, if there's a deep bay, your stick just bridges right over the mouth of it.
It skips it.
It skips it entirely. If there's a jagged peninsula jutting out, you might slice right across the neck of it. You're creating a polygon that roughly approximates the shape of Britain, but you're cutting corners. Literally.
So I'm getting a low-resolution version of the coast, like an 8-bit video game map.
Exactly. It's a low-res map. So you aren't satisfied. You decide to get more accurate. You swap your 100-kilometer stick for, say, a 1-kilometer stick.
Much smaller ruler.
A much smaller ruler. Now, you can walk into those bays, you can trace the curve, you can walk around those little headlands. You're hugging the shape much more tightly.
And common sense says I'm getting a more accurate measurement. A better number.
You are. But here's the kicker. Because you are now measuring all the ins and outs that you skipped before, the total distance you walk goes up significantly.
Okay, that makes sense. I'm including more details so the number gets bigger. I'm with you so far.
But let's keep going. You're a perfectionist. You swap the 1-kilometer stick for a 1-meter yardstick. Now you're walking around individual boulders on the beach. You're tracing the edge of large rocks that make up the cliff face.
And the length just, it explodes in it.
It explodes. Now, what if you use a ruler that's 1 centimeter long?
Now I'm tracing the outline of individual pebbles. The little jagged edges of a single stone on the beach.
Wait, on perimeter.
You're tracing the grains of sand, and then the molecules, and then the atoms that make up the sand.
If you follow this to its logical conclusion, if you use a ruler that is infinitely small, what happens to the length?
The length of the coastline of Britain becomes infinite.
Exactly.
Okay, stop there. That's the part that breaks my brain. Britain is an island. It's finite. I can fly across it in an hour. It fits on a map. It has a specific area, so many square miles. How can something with a finite area have an infinite perimeter?
That paradox is the doorway. It's the key to everything we are discussing today. That is the aha moment. In traditional geometry, it's geometry we learned in high school, with circles and squares, That shouldn't happen.
Right. It feels like it breaks the rules.
But in the real world, it does happen.
Yeah.
And that paradox introduces us to the central theme of our deep dive, fractals.
Fractals.
Oh,
Okay. We've all seen the posters, right? The tie-dye, psychedelic, swirling shapes that look like dragon tails or something from the 60s. But based on the reading, fractal isn't just a word for trippy art.
not at all.
It's a description of the architecture of the universe.
It is. In a nutshell, it's the geometry of nature.
So let's define our terms, because when
Uh-huh.
I was reading the source material, specifically Benoit Mandelbrot's book, The Fractal Geometry of Nature, he seems to have a real beef with the Greeks. He really goes after Euclid.
He does. And for good reason. Think about the geometry you learned in school. Euclidean geometry. What are the shapes?
Squares, triangles, circles, cones, spheres.
Right. And what are the characteristics of all of those shapes? They're smooth, a circle is perfectly round, a line is perfectly straight, a plane is perfectly flat. It's the geometry of an architect's blueprint. It's ideal, it's perfect.
It's clean.
But then you look out the window. Is the world clean?
No, it's a complete mess.
Benoit Mandelbrot, who's really the father of fractal geometry, he had this famous quote, and it's the cornerstone of this entire field. He said, "Clouds are not spheres, mountains are not cones, coastlines are not circles, and bark is not smooth, nor does lightning travel in a straight line."
So Euclidean geometry is like the Instagram filter version of the world. It's the idealized, smoothed out version that doesn't actually exist.
Exactly. And fractal geometry is the raw, unedited footage. It's the study of roughness. But here's the important part. It's not just random roughness. It's a specific kind of organized roughness.
Let's break that down then. The source material mentions 3 key characteristics that make something a fractal. If I'm looking at something, how do I know if it's a fractal or if it's, just a mess?
The first and most important characteristic is self-similarity.
Which means?
It's the idea that the pattern repeats itself at different scales. The part looks like the whole.
Okay, give me a concrete example from the real world.
The fern leaf is the classic biological example. Picture a fern frond. It's that long triangular shape made of leaves.
Got it.
Now, in your mind, break off one of the branches near the bottom. Hold it up. What does that little branch look like?
It looks like a mini fern, a smaller version of the whole thing.
Exactly. And if you squint and look closely at one of the tiny leaflets on that branch,
It looks like a tiny version of the branch, which in turn looks like the whole fern.
that is self-similarity. It's a nesting doll structure. It's a recursion. In pure mathematics, this can be exact. If you look at a mathematical object like the Koch snowflake, which we'll definitely get to, the zoomed-in version is literally a perfect, identical copy of the zoomed-out version.
But nature is messier than that, isn't it? A coastline doesn't have the exact same bay repeating over and over again.
Right. That's a crucial distinction. In nature, we call it statistical self-similarity. The coastline looks equally rough at all scales.
Equally rough.
Yeah. If I showed you a photo of a rocky coastline, but I cropped out any reference points, no cars, no people, no banana for scale, you wouldn't be able to tell me if the photo was taken from a satellite looking at 100 miles of coast, or from a drone looking at 1 mile, or if I was standing on a ladder looking at 10 feet of rock. The texture of the jaggedness is consistent, no matter the zoom level.
That's wild to think about. We usually rely on smoothness to tell scale. A billiard ball looks smooth from far away, but you see the imperfections under a microscope. A fractal looks just as rough no matter how close you get.
Which leads us directly to the second characteristic, scaling. This is the idea that zooming in reveals more detail, not less.
In a normal photo, if I zoom in, eventually I hit the pixels, I hit a blur, it just gets fuzzy.
Right. Because the photo has a limited resolution. But a true, ideal fractal has infinite resolution. You never hit the bottom. You never hit a smooth line. It's just, turtles all the way down.
Okay, so we have self-similarity and scaling, but now we have to tackle the third one. And I'm going to be honest, this is the one where I really struggled with the reading. Fractal dimension.
You are not alone. This is the concept that usually trips people up. It's a bit of a mind bender.
The notes talk about the Hausdorff dimension and things being 1.26 dimensions. That sounds like nonsense. I know what 1D is, it's a line. I know what 2D is, it's a piece of paper. I know what 3D is, it's a box. How can you have a dimension in between 1 and 2? What is that?
Okay, let's try a thought experiment. Imagine a ball of string, a big ball of yarn,
Okay, picturing it.
from way across the room. What does that ball of string look like?
It just looks like a point. A dot. 0 dimensions.
Right. Now, walk a little closer. Now you can see it's a ball. It occupies space. It looks like a 3D sphere.
Sure, okay.
Now, walk incredibly close. pick up the string and stretch it out. What is it now?
It's a line. It's one-dimensional.
But wait. Look at that string under a microscope. It's not a perfect line.
Yep.
It's made of fibers twisted together. It has thickness. It has width. It's 3D again.
You're just messing with me now.
No, I'm showing you that dimension can depend on your perspective, on your scale. But mathematically, a fractal dimension measures how efficiently a shape fills space.
Fills space. Unpack that for me.
Let's go back to the coastline. At its heart, it's a line, right? So you'd think it should be one-dimensional.
Yeah.
But it's so wiggly, so jagged, so crinkly, that it starts to take up more room than a simple straight line. It starts to encroach on the territory of a surface, a 2D plane.
So it's acting greedy. It wants to be bigger than it is.
In a way, yes. It's trying to be a 2D shape, but it can't quite get there. It never fully fills the plane. It's stuck in the middle. So we say it has a fractional dimension. The coastline of Britain, for example, has a dimension of about 1.25.
So it's more than a line, which is 1, but it's less than a plane, which is 2.
Exactly. It's a measure of its wiggliness or its complexity.
That actually helps a lot. The rougher and more complex the shape, the higher its fractal dimension.
Precisely. A smooth rolling hill might have a dimension just over 2, maybe 2.1. But a jagged, spiky mountain range that's almost impossible to climb might have a dimension of 2.7. It's almost filling the 3D volume with rock.
So these weird numbers, 1.26, 2.7, they aren't just abstract math. They are a literal measurement of complexity.
Exactly. And this allows us to do some really cool math. Let's look at the Cox snowflake you mentioned earlier. This is kind of the hello world of fractals.
Describe it for someone who can't see it right now.
Okay, you start with a simple equilateral triangle. Flat, boring Euclidean triangle.
Yeah.
Now you take the middle third of each of the 3 sides, you remove that segment, and you replace it with 2 sides of a smaller triangle pointing outwards.
So now I have a 6-pointed star, like a Star of David.
Right, but now look at the 12 little straight lines that make up that star. And you do the same thing to every single one of them. You take the middle third of each of those lines, and you grow a tiny new triangle out of it.
Okay, now it's getting really prickly. It's starting to look like a snowflake.
And you just keep doing it. Do it again and again and again. Forever.
What happens when you do it infinitely?
2 incredible things happen. The perimeter, the outline, gets infinitely long, just like the coast of Britain. But the area inside remains finite. It will never get bigger than a circle drawn around that original triangle.
So again, infinite border, finite space.
That's the paradox.
Yeah.
And its dimension is 1.2618. It's a line that has gotten so crinkly and complex that it's starting to act like a surface.
There's another one in the notes that I have to admit creeped me out a bit. The Menger sponge.
Oh, the Menger sponge is fascinating. It's the 3D version of this idea. Imagine a solid cube, like a Rubik's Cube, divided into 27 smaller cubes, 3 by 3 by 3.
Got it.
Now, you remove the cube in the dead center, and you also remove the center cube of each of the 6 faces. You basically punched holes all the way through it from every direction.
Okay, so it looks like a block of Swiss cheese, but with square holes.
A good way to put it. Now, take the 20 smaller cubes that are left and do the exact same thing to each of them. Punch holes through their centers.
And just keep going.
Keep going forever. As you do this, you are removing volume with each step. Eventually, if you do this an infinite number of times, the volume of the sponge actually reaches 0.
It disappears. It's gone.
The volume disappears. There is no stuff left inside. However, the surface area of all those infinite internal holes approaches infinity.
Wait, so it has 0 volume but infinite surface area? That's not possible.
It is in fractal geometry. It is a shape made entirely of skin and holes. Its dimension is about 2.72. It's almost a solid 3D object, but it's completely empty.
That sounds like a paradox straight out of a Borges story or something.
It does. And for a long time, that's exactly how mathematicians treated these shapes. They treated them like horror stories.
This brings us to the history section, which I found surprisingly dramatic. I kind of assumed Mandelbrot just sat down at a desk in the 70s and invented all this. But these shapes have been haunting mathematicians for centuries.
Oh, absolutely. We're talking about the era of mathematical monsters.
Monsters? They actually called them that.
That's what they called them. You have to understand the mindset of, say, the 19th century. Mathematics was about calculus. And calculus, at its heart, relies on things being smooth. You need to be able to draw a tangent line, a slope, at any point on a curve to understand its derivative.
Everything had to be smooth and predictable.
Right. But then, around the late 1800s, you had these rebels, guys like Carl Weierstrass and Georg Cantor, and they started cooking up these functions that just broke the rules. Weierstrass created a graph of a function that was continuous, meaning you could draw it without lifting your pen, but it was jagged everywhere.
So there was nowhere to put the tangent line, no slope.
Exactly. You zoom in, and it's jagged. Zoom in again, still jagged. Infinitely jagged. It was nowhere differentiable.
And the mathematical establishment did not like this.
They hated it. They were horrified. Charles Hermite, a very famous French mathematician of the time, wrote, and this is the real quote, "I turn away with fright and horror from this lamentable evil of functions which do not have derivatives."
Lamentable evil. He's talking about math like it's a demon from hell.
They viewed these shapes as pathological. They thought they were ugly exceptions, freaks of nature that had no place in the beautiful, orderly world of mathematics. They were bugs in the system that needed to be ignored.
So you have these outcasts, Cantor, Peano, Helga von Koch, toiling away in the shadows, creating these monsters.
Cantor was a particularly interesting and tragic figure. In 1883, he created the Cantor set. Imagine a line segment. You just wipe out the middle third.
Okay, so now I have two smaller lines with a gap.
Right. Now wipe out the middle third of both of those. Now you have 4 even shorter lines. You just keep doing that forever.
You're basically turning a solid line into dust.
Precisely. You end up with a dust of points. The total length of all the remaining pieces is 0. But it still contains an infinite number of points. It just completely defied intuition at the time.
So why didn't these guys discover fractal geometry back then? They clearly had the shapes.
They lacked 2 things. First, they lacked the unifying concept. They didn't see these as a new class of geometry. They just saw them as individual oddities, as monsters in a cabinet of curiosities. But more importantly, they lacked eyes.
Eyes.
They couldn't see what they were doing. They were working with pen and paper. To calculate and draw even a few iterations of a fractal by hand takes a lifetime. They could write the formula, but they could never truly visualize the result, the infinite complexity.
And then enter Benoit Mandelbrot.
Enter Mandelbrot. And just as importantly, enter IBM.
The computer company.
The very same. In the 1960s, Mandelbrot wasn't working at a university like the others. He was a research fellow at IBM. And at IBM, he had access to something the 19th century mathematicians could only dream of. Mainframe computers.
He could finally crunch the numbers.
He could crunch them, and he could plot them. He could tell the computer to print them out. He took these monster equations, these recursive formulas that others had found so pathological, and he fed them into the machine. And when the printer started spitting out the images...
He didn't see monsters.
No. He saw mountains. He saw coastlines. He saw the branching of trees, the patterns in clouds. He realized that these pathological shapes looked exactly like the real world.
That must have been an incredible shiver down the spine moment, realizing that the broken math was actually the math of reality.
It was the paradigm shift.
Yeah.
So in 1975, he finally gave it a name. He coined the term fractal from the Latin word fractus, which means broken or fractured. He was reclaiming that brokenness. He was saying, the world isn't smooth, the world is fractured. And here is the math to describe it.
And the icon of this entire revolution is the Mandelbrot set. We have to talk about the beetle.
The beetle, the Buddha, the cardioid. It's been called many things.
This is the image that launched a million screensavers and posters. But what is it, really?
It's a picture. It's a map of surprisingly simple equation. Vn plus 1 plus 1 plus bln plus c.
Okay, don't just gloss over that. Zn plus 1 plus 1 plus c That looks incredibly simple. It's like something you'd see in high school algebra.
It is simple. It's a feedback loop. You take a starting number, you square it, you add a constant, c in dollar, and you get a result. Then you take that result and plug it back into the beginning of the same equation. And you do it over and over and over.
Iteration.
Right. Now, Mandelbrot didn't do this with regular numbers. He did it with complex numbers, which can be plotted on a 2D plane.
The numbers with a real part and an imaginary part.
Correct. For every single point on the graph, every pixel you're in this equation, if the number stays small after many iterations, if it stays trapped and doesn't fly off to infinity, you color that pixel black.
And that's the beetle shape in the middle.
That's the black shape. If the number does explode off to infinity, you color the pixel based on how fast it explodes. And that's what creates the beautiful, psychedelic swirling colors around the edge. That's the escape set.
And the complexity of that edge, that boundary between the black and the color, is infinite.
Utterly infinite. You can zoom into the edge of the Mandelbrot set for 1 trillion years, and you will never run out of new patterns. You will see spirals and seahorse tails and lightning bolts, and eventually you'll see tiny, perfect replicas of the original beetle shape hidden deep in the valley of a spiral.
All from square it and add C.
That's the profound lesson of the Mandelbrot set. Infinite, mind-boggling complexity can arise from incredibly simple rules. You don't need a complex blueprint to build a complex world. You just need a simple rule and a feedback loop.
That feels like a perfect segue. Because if simple rules create complex shapes on a computer screen, surely nature figured this out a long time ago. Let's move to section 3, fractals in the natural world.
Let's do it.
Hmm.
Because once you put on these fractal glasses, you honestly never see nature the same way again.
Let's start with the inanimate stuff, rocks, clouds, and lightning.
Lightning is such a visceral example. Think about what lightning is actually doing. It's a massive discharge of electricity trying to get from the cloud to the ground. But the air isn't a vacuum. It's full of dust, humidity, different temperatures. It's an obstacle course.
So the bolt has to feel its way down through the path of least resistance.
Exactly. It doesn't happen all at once. It moves in steps, called stepped leaders. It finds a path. It branches. Then those branches face new resistance, so they have to branch again. The shape it creates is called a Lichtenberg figure. That jagged forking pattern is the most efficient way to equalize that massive electrical charge across a resistant medium.
So it's the visual record of the struggle between energy and resistance.
That is a beautiful way to put it. And we see the exact same pattern in river deltas. Water wants to get to the ocean, the ground resists, so the river branches and fans out to find the most efficient network of paths.
I want to talk about snowflakes, because the old adage is no two snowflakes are alike. But is that true? And why?
It is true, and the reason is purely fractal. A snowflake's formation is a battleground between two competing forces. On one side, you have order. Water molecules want to freeze into a stable crystal lattice. And for water, that's a hexagon. That's why all snowflakes have 6 sides, or 6 points.
Okay, that's the faceting part, the orderly part.
Right. But on the other side, you have chaos. This is the branching. As the tiny ice crystal falls through the cloud, its 6 corners stick out just a little bit further into the moist air than the flat sides do.
They're more exposed.
Yes. So they accumulate new frozen water vapor faster. This creates an instability, which causes a branch to shoot out from the corner. But then the tip of that new branch sticks out even further, so branches shoot out of the branch.
Recursion again.
Exactly. But here is the key. The snowflake is tiny, and it's falling through a turbulent cloud. The temperature and humidity are changing every single millisecond.
So the instructions for how to grow are changing constantly.
The environmental input is constantly changing. Now, the 6 arms of a single flake grow symmetrically because the flake is so small. All 6 arms are experiencing the exact same temperature and humidity at the exact same moment, so they grow in sync.
But no two flakes are alike because...
Because no 2 flakes take the exact same path through that cloud. One might fall a little to the left, hit a dry patch, then a super humid patch. Another one, falling 10 feet away, has a totally different history. The final shape of the snowflake is literally a physical recording of its unique journey through the sky.
That's actually kind of poetic. It's data storage in ice crystal form.
It is. A story written in ice.
Okay, let's look at something alive. Trees. We all draw them as fractals when we're kids, right? A stick, then a V, then V's on the V's. But why? Evolution doesn't care about looking cool. Why did trees evolve to be fractal?
It's a classic engineering problem. Imagine you are a tree. You have 2 main goals. 1, capture as much sunlight as possible. That means you need to maximize the surface area of your leaves.
Okay, more solar panels.
Exactly. Goal 2, you need to transport water and nutrients from the ground all the way up to those thousands of leaves.
Yeah.
But pumping water is metabolically expensive. Building wood is expensive. You want to minimize the transport distance and the total mass of the structure.
So you have a trade-off. Maximize the surface area, but minimize the volume and transport energy.
And guess what shape is the mathematically optimal solution to that problem?
A fractal.
A branching fractal. It is the perfect solution for filling the air with solar panels while using the minimum amount of wood to hold them up and service them. It's an optimization algorithm that's been field tested for millions of years.
So nature found the math long before we did.
Nature is the math. We just found the language to describe what it was already doing.
There is one vegetable that seems to have taken this to an extreme, the Romanesco broccoli.
Ah, the alien vegetable, the superstar of fractals.
If you haven't seen this thing, you have to look it up. It's neon green, and it's a cone made of spiraling cones that are made of smaller spiraling cones. It looks like it was designed by a computer. It doesn't look real.
It's the most visibly perfect fractal object you can hold in your hand. And the biological story behind it is actually kind of funny. It's a genetic mistake.
A mistake? It looks so perfect.
It's a failure to flower. In a normal broccoli or cauliflower, the plant produces a bud that is supposed to become a flower. But in Romanesco, the genetic instruction misfires. So instead of making a flower, the bud tries to make a new stem.
It resets the program.
It resets. But then that new stem tries to make a flower, fails, and makes another stem. This error repeats recursively, over and over, creating that perfect self-similar spiral.
So the incredible spiraling mathematical beauty of the Romanesco is basically a genetic stutter.
In a way, yes. It's a beautifully broken feedback loop that accidentally creates a masterpiece.
This whole concept of optimization seems to be the bridge to our next section, because if trees and plants use it to survive, then humans probably use it too.
We are talking fractals, my friend.
Let's get into the body. Section 4, the fractal human. The stat that absolutely blew my mind in the source material was about the human lungs.
The tennis court.
Yeah, the tennis court. Walk me through that because it sounds impossible.
Okay. Your body needs oxygen to live. To get oxygen into the blood, you need contact between the air you breathe and your blood vessels. You need surface area. If your lungs were just two empty balloons, two smooth bags in your chest, the surface area would be tiny. You'd suffocate almost instantly.
You wouldn't be able to absorb enough oxygen with each breath.
Not even close. So evolution had a packaging problem. How do you pack a massive surface area into the small, confined volume of the chest cavity? The answer, you branch. The trachea branches into bronchi, which branch into bronchioles. It goes on for about 23 levels of branching. By the time you get to the tiny air sacs at the end, the alveoli, you've created a surface area about 100 square meters.
Which is roughly the size of a tennis court.
Folded up neatly inside your chest, it's a classic space-filling curve. It's a fractal solution to a fundamental biological problem.
And the same logic has to apply to our blood, right? The circulatory system.
It has to. Every single cell in your body, from your brain to the tip of your toe, needs to be supplied with oxygen. So a blood vessel, a tiny capillary, has to be within a few microns of every single cell. But your body can't be made of 100% blood. It would be too heavy, too inefficient.
So you need a network that reaches everywhere but takes up very little space.
Exactly, a fractal network.
Yeah.
And this leads to something amazing called Kleiber's law. This is one of the few things in biology that you can actually call a law, because it holds up almost everywhere, from a mouse to an elephant.
With the 34 rule.
The 34 rule. If you take a mouse and an elephant, the elephant is thousands of times bigger. So you'd think, okay, if the elephant is 10,000 times heavier, it needs 10,000 times more energy to live.
That would be linear scaling. Makes sense.
But it doesn't work that way. It's much more efficient. An animal's metabolic rate scales to the 34 power of its mass, not to the power of 1. For decades, scientists didn't know why that specific number, 34.
And the answer is fractals.
The answer is the geometry of the delivery network.
Huh.
Physicists Geoffrey West and James Brown proved that because the circulatory and respiratory systems branch in a fractal, space-filling way, they essentially add a fourth dimension of efficiency to our 3D bodies. The mathematics of that fractal network yields that 34 exponent exactly.
Wow. So we are efficient because we are fractal.
We can exist at our scale because we are fractal.
That brings me to the brain, the most complex object in the known universe.
The ultimate fractal.
I was looking at the notes on neurofractals, and this is fascinating. It mentions that a healthy brain has a specific fractal dimension, and that in certain diseases, that dimension changes.
This is really the frontier of neuroscience right now. Structurally, the brain is obviously fractal. The cortex is folded, that's called gyrification, to maximize the surface area of our gray matter. If you flattened out a human brain, it would be the size of a large pillowcase. We crinkle it up to fit it inside the skull.
It's the Coastline paradox again, just with brain tissue.
Exactly. But it goes deeper. Look at the individual neurons, the dendrites, the little fingers that reach out to connect to other neurons. They branch in incredibly complex fractal patterns. Yeah. And what researchers are finding is that in neurodegenerative diseases like Alzheimer's or MS or ALS, that branching structure simplifies.
It simplifies, it gets less complex.
The fractal dimension literally drops. The neurons lose their roughness, they become smoother, less connected, less efficient.
So a smooth brain is literally a dying brain. That's a terrifying thought.
In a way, yes. Complexity is health. Loss of complexity is pathology. But it's also hopeful, because it means we might be able to detect these diseases much earlier just by doing a fractal analysis of an MRI scan.
Before we leave the human section, we have to talk about fractal fluency, because this, to me, explains why I hate modern minimalist architecture and why I feel so good when I'm walking in a forest.
The biophilia hypothesis, it's a powerful idea.
The idea is that we evolved in nature. We didn't evolve in square, concrete rooms with blank walls.
Right. For millions of years, our ancestors' visual systems were processing fractal trees, fractal clouds, fractal horizons, the patterns of light on water. Our visual cortex evolved specifically to be good at processing that kind of data.
We are tuned for it, like a radio to a specific station.
We are fluent in the language of fractals. And studies have shown that when you look at a fractal pattern with a dimension between 1.3 and 1.5, which is typical of a natural skyline or a cloud formation, your brain enters a state of wakeful relaxation.
The alpha waves kick in.
Your physiological stress levels, measured by skin conductance, can drop by up to 60% just by looking at a certain kind of pattern.
This brings up Jackson Pollock. I have to admit, I've always been one of those people who looks at a Pollock drip painting and says, my 5-year-old could do that.
You and almost everyone else. But here's the thing. Your 5-year-old can't.
Why not? It's just splashing paint.
Because Pollock wasn't just splashing paint randomly. He was consciously or unconsciously engaging in a process that mimicked the fractal mechanics of nature. Physicists have analyzed his drip paintings. They are unequivocally fractal.
They have a measurable fractal dimension.
They do. And what's really interesting is that as his career progressed and he became more skilled in his technique, the fractal dimension of his paintings increased. They became denser with complexity, getting closer and closer to the fractal density of a complex forest canopy.
So when we stand in a museum and stare at one of his huge canvases, we aren't admiring the mess. Our brain is getting a subconscious hit of nature.
Your brain is resonating with a familiar structure. It feels right to our visual system because it matches the very structure of our own brains and the world we evolved in.
That is the single best explanation of abstract art I have ever heard. Okay, so we've done nature, we've done the human body. But we humans are tool builders. We don't just admire fractals, we use them. Let's move to Section 5, Technology and Practical Applications.
This is where the rubber really meets the road. It's easy to get lost in the philosophy of it all, but fractals are incredibly practical.
I love the story of the fractal antenna. It feels like a hacker story from a movie.
It is. It's a great story. Nathan Cohen, 1988. He was a radio astronomer and a ham radio enthusiast. He wanted to set up a powerful antenna system at his apartment in Boston.
But there was a problem.
The landlord, the classic villain. The landlord said, "Absolutely not. I don't want giant, ugly metal spikes all over my roof."
The eternal struggle of the renter.
So Cohen got creative. He knew about fractals from his astronomy work. He thought, wait a minute, if a fractal curve packs an infinite length into a small space, like the coastline of Britain, maybe I can pack a huge amount of electrical wire into a tiny antenna.
He folded the wire up on itself.
He bent it into a specific fractal shape called the Minkowski curve. He essentially crumpled the wire up, but in a mathematically precise way. He made it small enough to fit in the box, glued it to a board, and stuck it up on the roof, hidden away.
And did it work?
Not only did it worked better than the big, straight antennas.
How is that possible?
This is the genius part. A standard straight wire antenna is tuned to one specific frequency. Its physical length corresponds to a specific wavelength of radio wave. But a fractal antenna has self-similarity. It has big parts, medium parts, and tiny little parts, all in one structure.
So it can resonate with big waves, medium waves, and small waves all at the same time.
Exactly. It is inherently multi-band. It resonates efficiently at many different frequencies at once.
And this is why modern cell phones look the way they do.
Correct. Remember in the 90s, cell phones had those little pull-out antennas?
Oh, yeah, I miss snapping those off for fun.
Modern phones don't have them. The reason why is that inside your phone, etched onto a circuit board, is a tiny fractal antenna chip. It's an intricate recursive pattern. And that one tiny chip can talk to the cell tower, it can talk to your Wi-Fi router, it can talk to your Bluetooth headphones, it can talk to a GPS satellite, all different frequencies, all handled by one elegant fractal shape.
So I'm carrying a fractal in my pocket right now.
You couldn't have a smartphone without them.
That is so cool. Let's shift to the digital world. Computer graphics. As a gamer, this is close to my heart.
If you go back to the early 80s, computer graphics were, well, they were geometric.
They were blocks. Mountains looked like perfect pyramids. Trees were cylinders with spheres on top.
It looked fake because it was too smooth. It was Euclidean. Then comes Lauren Carpenter. He was working at Lucasfilm, which would become Pixar. They were making the movie Star Trek II, The Wrath of Khan, and there's that famous scene, the Genesis effect, where a dead moon is terraformed into a lush planet in a matter of seconds.
I remember that sequence. It was absolutely mind-blowing at the time.
Carpenter used fractals to create those landscapes. He didn't have an artist sit there and sculpt every single mountain and valley. He wrote an algorithm.
Yeah.
He basically told the computer, Start with a big triangle. Break it into 4 smaller triangles. Displace the center point randomly up or down. Now repeat that process on the smaller triangles.
He taught the computer how to be rough, how to be natural.
He taught it the basic rules of erosion and geology in mathematical form. And the result was the first photorealistic computer-generated landscape in film history.
And now, every modern video game uses this same principle.
It's called procedural generation. When you play a game like No Man's Sky or Minecraft, the computer isn't storing a map of the entire universe on your hard drive. It's storing a fractal seed, a simple equation. And when you fly to a new planet, the math generates the mountains and rivers and coastlines in real time based on that seed.
It's the ultimate form of data compression. Infinite, non-repetitive worlds stored in a single equation.
Exactly.
Speaking of life and death applications, there's one more I want to touch on from the notes. Cancer detection. We talked about how the healthy brain is fractal, but tumors apparently are different.
This connects right back to the circulatory system. Tumors grow incredibly fast. They're aggressive. They need a lot of blood to fuel that growth, so they stimulate the growth of new blood vessels, a process called angiogenesis.
But because they're growing so fast and chaotically,
They're messy about it. A healthy blood vessel network is an organized fractal. It has a clear hierarchy. Big arteries branch to smaller arterioles, then to tiny capillaries. A tumor's blood vessel network is just chaos. It has weird loops, dead ends, tangles. It's inefficient.
it's bad geometry.
It's disordered chaos versus the organized chaos of healthy tissue. Doctors can now run software that analyzes the fractal dimension of the blood vessels on a scan, like an angiogram. And they can look at the math and say, with high confidence, that's a tumor, without ever having to cut the patient open.
That is absolutely incredible. It's literally math saving lives.
It really is.
We've covered so much ground, from the coast of Britain to the neurons in our brains to the phones in our pockets. But I want to zoom out for this final section, section 6, chaos theory and the bigger picture.
We can't really talk about fractals without talking about chaos theory. They're two sides of the same coin. Fractals are often called the pictures of chaos.
We mentioned the butterfly effect a little earlier.
Yeah. The butterfly effect is the classic example. It's the idea of sensitive dependence on initial conditions. In any complex, chaotic system like the weather, a tiny, imperceptible change in the input, like a butterfly flapping its wings in Brazil, can cascade and amplify through the system and cause a tornado in Texas weeks later.
And fractals represent this visually. How does that work?
They do. Go back to the Mandelbrot set. If you pick a starting number, a point on that graph, and run the equation, you get a certain pattern. But if you change that starting number by just a tiny, tiny fraction, the smallest decimal place you could imagine, the resulting pattern can be completely different. But here is the paradox, and this is what keeps philosophers and physicists up at night. The Mandelbrot set is generated by a totally deterministic equation, Cn plus 1 plus 1 plus Cn2 plus C dollar. It's fixed. The outcome for any given point is predetermined.
But it looks infinite and unpredictable.
Exactly. It produces infinite, unpredictable-looking complexity from a rigid, simple rule. It suggests that the randomness we see in the world, the shapes of clouds, the flow of rivers, maybe even the stock market, might not be truly random at all. It might just be the result of a simple, deterministic rule playing out over and over and over again. Order and disorder aren't opposites. They're generated by the same process.
That is a very heavy thought. Before we wrap this up, I want to touch on the cultural side of this. We often think of fractal geometry as this Western mathematical discovery from the 1970s, with Mandelbrot and IBM. But that's not the whole story, is it?
Not at all. We have to mention the work of Ron English on African fractals. He's an ethnomathematician, and he studied the architecture of indigenous African villages. And he found that they were consciously using fractal scaling in their designs long before Europe ever thought of it.
Can you give me an example?
Sure. He'd find a village laid out in a large circle. Inside that circle were circular family compounds. Inside those compounds were circular houses. And inside the houses were miniature circular spirit houses for the ancestors. It was circles within circles within circles.
Their cursive scaling, self-similarity.
And he found the same patterns in their textiles, in their sculpture, even in cornrow hairstyles. They developed a system of fractal geometry and mathematics completely independently, intuitively understanding that this structure represented community, strength, and continuity from one generation to the next.
It's like humans have always had an intuition for this geometry, even before we had the computers to prove it was real math.
Well, we are part of nature, so it makes sense that we would naturally mimic its deepest patterns.
So we've arrived at the end of our dive. We've gone from the infinite coastline to the fractal antenna. If you had to boil it down, what is the big takeaway here?
For me, it's about reframing how we see imperfection. For centuries, our science and our art were dominated by the idea that the smooth lines of Euclid were the standard of perfection. We tried to force the world into straight lines and perfect circles and boxes.
But the real world never quite fit.
No. And we used to think the roughness of nature, the jagged mountain, the branching tree, the turbulent cloud, was messy. It was random, a flaw. But what fractal geometry teaches us is that this roughness isn't a flaw, it's a feature. It's the universe's optimization code. It's how the universe maximizes efficiency, connectivity, and ultimately, life itself.
So it's actually efficient to be rough.
It is. And if our brains, our bodies, and the natural world are all built on this fractal geometry, then perhaps the messiness of life is actually where the beauty and the resonance lies. Maybe looking for straight lines in a fractal universe is the very reason we feel stressed, like we talked about with the biophilia hypothesis.
We're trying to force a fractal peg into a square hole.
Exactly. And maybe embracing the roughness is the key to finding our resonance with the environment.
That is a powerful place to land. So to you, the listener, I'll leave you with this final provocative thought. The next time you walk outside and you see a tree or you look up at a cloud, ask yourself, are you seeing a shape? Or are you seeing an equation in motion?
A living, breathing equation.
Thanks for diving deep with us. We'll see you next time.